Hello, everyone. Thanks for joining tonight's Grad Talk. Greetings to everyone. Today we are hosting Bushra Anjum. Excuse my pronunciation, Anjum, right? Bushra.
That's correct.
We have the same name in Turkey, Bushra, so that's fine. Easy to pronounce. So Bushra is very successful women in the field and science. So I guess it's just before a week before the International Women's Day, we had a good introduction by having you in our program. We are really pleased for that. So Bushra Anjum, Dr. Bushra is a health IT data specialist currently working as a senior analytics manager at San Francisco and joining our grad talk from San Francisco right now, right? And working at the firm Doximity. It's a health technology-based company, I guess. And she leads a team of analysts, scientists, and engineers in the company. Before that, prior to this job, she was working for Amazon as a software engineer, architecting large-scale distributed services, supporting Prime membership, with an emphasis on the performance and scalability. And formally, she is a Fulbright scholar from Pakistan and doing academic stuff and studies in both Pakistan and USA for many years before joining the industry. She continues to volunteer at Caltech State University campus and public school teachings CS-related content and serving as industry mentor. And alongside also, she is really active woman in the field. She is also serving as a community leader and mentor at Global Tech Women and Pakistani Women in Computing and CRA Widening Participation, Rewriting the Code, RTC, and Improved Leadership Alliance, Tech Girls, Code Girls, many women-related fields. So that I guess that will be perfect to have you next week, I guess. She received her PhD in computer science at North Carolina State and I want to make it brief, but you have a very long things done, so it's hard to summarize it. She has authored scholarly papers in the areas of performing evaluation, quality of service, predicting, provisioning of networks, data science, and big data analytics. Thank you, Dr. Anjum, and we are really happy to have you. So without further ado, we would like to listen your presentation and talk. So let me stop my screen and we are with you.
Thank you so much, Murad. Let me start the presentation. And I apologize to the audience for being a few minutes late. There is some construction going on in this area and somehow the connectivity is questionable for most of the day, especially early in the morning. Fine. It's 8 a.m. here. So yeah, thank you so much for inviting me here. It's really, really an honor to talk to the audience in the university in Turkey. Some of my best friends are from Turkey, and being from Pakistan, of course, the country and the culture is very, very close to my heart. We'll be talking about feature engineering for the most part of the session. Murad has already so kindly introduced me, so I'll just take a few seconds here. Originally, I'm from Pakistan, as I said. I did both my undergraduate and master's from there. And then in 2007, I came to the States for a PhD degree. After that, I was teaching for about 4 or 5 years, a couple of years back in Pakistan, a couple of years in the States, then made my switch to the industry, joined Amazon, then Doximity, where I currently am. So I joined Doximity as a data scientist, primarily because my PhD was in performance evaluation and queuing theory, so a mathematics background. And then at Amazon, I learned a lot about backend engineering and distributed systems. So data science seems to be the perfect field that can combine maths and engineering. And then about a year ago, I made my switch towards the management side of it. And currently, I'm the Senior Analytics Manager for Doximity. So I chose the topic of feature engineering, which is the bread and butter of machine learning. So machine learning is a very shiny, very exciting field, and a lot of people would want to go into that field or become machine learning engineers or data scientists. So what comes as a surprise to them often is that most of the work that we do as data scientists is actually very mundane and boring. It's not about shiny algorithms or all these fun numbers and model fitting. It's usually getting the data right, which comes into the realm of feature engineering. And that's what I'll be talking about for the next, say, 40-45 minutes. And then, of course, happy to take any questions. All right, so a couple of terminologies that we'll be using for the remainder of the presentation as well. So 4 things. What is a model? What are mathematical formulas? What is a feature? And what is feature engineering? So a model describes a relationship between various aspects of data. And that is something that we are familiar with. What's a machine learning model? It describes relationships between different aspects of the data. Models are at the very bottom, mathematical formulas. And what is a mathematical formula? It relates various numeric quantities to each other. And that's important. Let me go over that again. So model describes relationship between various aspects of data, and mathematical formula defines the relationship between various numeric quantities. Numeric is important. So then what is a feature? A feature is a numeric representation of raw data. Anything and everything that we want to be used in a machine learning model has to be converted into a numeric format. It cannot be text, it cannot be a picture, it cannot be a category, it cannot be a video or an audio, it has to be a number. Everything related to data has to be converted in a numeric format. And feature engineering is the process of formulating the most appropriate features into mathematical form, given the data, the model, and the task. So how do we take different aspects of data that may or may not be numeric and convert all of them into numeric format so that they can be then used by the algorithms or the mathematical formulas to give us the kind of predictions we want to make? So as we go forward in this talk, I'll be focusing on 3 main types of features that we use. First is the numeric features, the features that are already in a numeric format. Second is the text features, the features that come in the form of free-flowing English text. And the third is various categories, like a list of countries or list of cities. So various categories, how do we convert those into numeric format? I would like to emphasize again that the most of the work that we do as data scientists or machine learning engineers, about 80% of that falls into the realm of feature engineering. So Professor Andrew Nguyen, he was the founder of the Human Brain Initiative at Google, and currently he also has some of the leading courses on AI and machine learning on Coursera. And I really like his quote that coming up with the features is difficult, time-consuming, requires expert knowledge, and applied machine learning is basically feature engineering. That's 80% of what we do. So let's start with getting into the nitty-gritties directly, numeric features. So I said that feature engineering is about converting features into a numeric format, but if the feature or the data already is in the form of numbers, do we still need to do anything about it? Well, we do, and we'll talk about that. Why are some of those things important? The first thing is about numeric features. So let's say it's a number, minus 36, that we are using we want to use in our model as a feature. So first thing is the magnitude. Is the magnitude important? Is 36 important for us? Or does only the fact that the number is positive or negative, does only that matter? Or does 36 matter to us, or does only a binary representation of that 0, 1, will that be enough? Because the more simple the features are, the better our models perform, both in terms of how long they take to get the predictions out, but also how accurate are the predictions. The more data or the more variety of data we throw at the models, the more they try to find meaning out of it, and the less accurate sometimes our predictions become. So we want to give the model exactly the right amount of data, not more, not less. So then magnitude, is magnitude of the number important, or just is only sign important? Scale, what is the minimum and the maximum value of this particular feature that we are looking at? Scale is important in some models as opposed to the others. So if you're familiar with the Euclidean distance, and if you're not, let me just not cover that, just in case you're not. So any model that is a linear function of input is highly dependent on scale. So for example, if our model is, say, 3x plus 1, that whatever value of x we get, it outputs 3x plus 1. That model is extremely volatile to the scale of the input. If the scale is 1, the output is 4. If the scale is 100, the output is 301. So the scale becomes important in the models that are linear functions of the input. Or the other way we say that is that they are, which are based on Euclidean distance of the features. But scale is important. What's the minimum value? What's the maximum value of this feature? Third is the numeric distribution. What is the probability of taking a particular value for this feature? How does it look like in terms of probability distribution? And let me go over that a little bit more. So talking a little bit more about magnitude. Again, is the actual magnitude, as I was saying, 36, is it important, or will 0 and 1 suffice? For most of the features that we use, which talk about or which mark user preference, for example, interested, not interested, clicked, not clicked, viewed, not viewed, those features are usually best categorized as binary features, so a 0 and a 1. Most of the time, it's more important to know whether a user is interested or not interested, as opposed to how many times the user actually clicked on a particular card. So that's one thing that a lot of domain knowledge comes into play when we are deciding on the feature, that whether a binary representation is okay, or do we actually need the magnitude. If we don't need the magnitude, getting to 2 values is almost always simpler and leads to better predictions. Do we need to binarize the number? And second is, do we need to quantize the number, which is also called binning, which means that we may have a number which has continuous values going from, say, 1 to 100. Do we need all these 100 values? Or can we bin those values, say, into 10 bins? That value 1 to 10 goes into bin 1, value 11 to 20 goes into bin 2, so on and so forth. So then instead of 100 unique values, we will end up with 10 unique values. Model becomes simpler, predictions become better. Can binning work for our case? And binning could be of 2 types, fixed width binning and adaptive width binning. So fixed width is when we are making equal divisions of the x-axis, if you will, the kind of example I gave you, going from 1 to 10, then 19 to 20, so on and so forth. We are making a fixed length buckets of the x-axis. Adaptive binning is when we are making fixed buckets, but of the data, that in each bucket, there are equal points of data. Let's say we make 4 buckets, and in the first bucket, 25% of the data lives. In the second bucket, the next 25% of the data lives, third and fourth, so on and so forth. And if you look at the graph on the very right, the bottom right side, and look at the red lines, that's an example of adaptive width binning. Now the x-axis division is not equal, but the data that falls within each bin is equal. So those are the 2 main forms of binning or quantization we do, dividing the x-axis into equal intervals, or dividing the data into equal intervals. If we divide the x-axis into equal intervals, the data that will fall in each of the bins will not be the same. And if we divide the data into equal bins, the actual length of the interval will not be the same. Again, 2 excellent techniques, takes a lot of data and then that captures it or puts it into a small amount of buckets, makes our feature engineering better. The second technique or the consideration is about the scale, that what's the minimum and maximum value of the data. If the minimum and maximum value really are important, good. But if they are not important, only their spread is important, then it's good to normalize those values. one of the simplest way to normalize the values is called the min-max scaling, where you take a value and minus the minimum value from it and divide it by the max minus min. So basically it takes the entire data and that brings it down to into the interval of 0 to 1. So the spread remains the same, but instead of going from, say, value 1 to value 10,000, now it is limited into the value 0 to 1. Another kind of scaling is called variance scaling, and that comes with the knowledge of probability distributions and also the normal distribution, that we are dividing the spread by the variance of the data, and it also brings the data into a distribution which has zero mean and one variance. The third kind of scaling is called L2 scaling. I'll not go into a lot of detail of that, but L2 normalization is basically about taking the data points and transforming it such that they are at a unit vector distance from the origin. So if you can see into the figure, the top figure, the blue dots were almost spread all over the 4 quadrants, but after this normalization, they are all at a place which is at a unit distance from the origin. So the standardization, the variance scaling, and the L2 scaling are more mathematically advanced concepts. A min-max scaling is easy to visualize and understand, but the basic concept is the same. That is the maximum value important to us? Or can we bring that maximum value into a certain kind of a scale that can still keep the important features of the data, but we don't have to take all that the entire scale into consideration? The numeric distributions are important to understand. I'll not go over a lot of details of these. Of course, the entire probability courses are spent on understanding these distributions. However, if you are new to the field or interested in the field, I would recommend learning about 5 distributions that are usually 90% of the time we use those distributions in most of our work. Binomial, Poisson, and normal. And if you remember from any probability course that you may have taken, binomial distribution is kind of the main distribution. Poisson distribution is a limiting case of binomial, and also normal distribution is a limiting case of the binomial distribution. I will not go into the mathematical details of it in favor of time, but binomial, Poisson, and normal, these 3 distributions we deal with a lot when we are doing feature engineering work or machine learning work. And it's important to realize how these 3 are related. As I said, both Poisson and normal are limiting cases of binomial distribution. And then the other set is Poisson, exponential, and gamma distributions. They are all part of a process which is called a Poisson process. They all look at that process in different ways with different angles, but they are also related to each other. Poisson, exponential, and gamma distributions. They cover most of the skewed distributions that we look at. By skewed, I mean heavy tails distributions, or distributions which are not equally spread on both sides, but they are elongated on a single side. So whenever you are looking at feature engineering or data science, or if you would like to get into that field, having familiarity with these 5 distributions and knowing how they relate to each other is extremely important, because various machine learning models that we use have certain assumptions built into them, that the data that will be coming in will be normally distributed, or the data that will be coming in will have a long tail distribution. And if the data that is coming in does not have that kind of distribution, it messes up the algorithm. So numeric distribution is the third aspect of numeric features that we need to be careful about. Coming to the more interesting features, the text features, which are actually not in numbers format to begin with, then what do we do about that? The most simplest technique that is being used is called term frequency. It's also called bag of words. You may hear both terms being used. And it's simply the number of times a particular word appears in a document. So a simple count of that. That's how we are converting a word into a number. How does it look like? So let's say we have these 3 reviews or 3 documents, 3 movie reviews. They're more or less similar, but still have a few different words. So what do we do in the term frequency or bag of words technique is that we make a matrix with one column per unique word. So here's the matrix representation. So we took all the words that are present in these 3 sentences and we make one unique column per word. And then we assign a number to each of those unique columns. So the word this gets a number 1, the word movie gets a number 2, so on and so forth. There are actually 11 words in these 3 sentences. And then we count the number of times that particular word has appeared in that particular document. Here we are using just sentences, so I'll just say sentence, but usually this technique is for documents, various web pages, if you will, or various documents. So we can see that for review 1, this movie is very scary and long. We have the word this appears 1 time, so it's 1. The word movie appears 1 time, so that's 1, so on and so forth. The word spooky does not appear in the first sentence, so it has a count 0. Similarly, the word good does not appear in this sentence, so it has a count 0. However, we still have these words because they appeared in some document or some sentence, even not in the review 1 sentence. And then similarly for review 2 and review 3, we get a count of these words per document. And then as a feature, what goes into the machine learning algorithm is this matrix of 1s and 2s and 0s. So that's how we are converting a textual format of input, which may come from different documents, converted into a matrix format where the column of the matrix, each column of the matrix corresponds to a unique word, and each row of the matrix corresponds to a unique document, and then the counts of the words in that document. And that goes in as a feature. A couple of interesting caveats there, however. Let's say we have 2 sentences, man bites dog and dog bites man. If we go into the journalistic lingo, dog bites man is not news, but when man bites dog, it is news, which is to say that these 2 sentences are not equivalent, even though they are using the same words. Again, going back to our term frequency or bag of words representation, since both these sentences have overall 3 unique words, so our matrix will have 3 columns, man bites dog, and the representation of sentence 1 will be 1, 1, 1, and the representation of sentence 2 will also be 1, 1, 1. So when that matrix goes into a machine learning algorithm, it is losing context. As I said, the sentence 2 is less informative than sentence 1. Man bites dog is a news, dog bites man perhaps is not a news. So when we use this technique of term frequency or bag of words, we lose context because context comes from a group of words, not individual words. Okay, so how do we manage context then? So how about instead of having 1 word per column, which is called unigrams, uni means 1. So instead of having 1 word buckets, how about if we get 2 word buckets, which are called bigrams? That means that we don't only take a single word at a time, we take all unique combinations of 2 words at a time. So for these 3 words, we can have 7 unique combinations. Man bites, man dog, bites man, bites dog, dog man, dog bites. So these are all the unique 2 word combinations that we can create out of these 3 words. And then we try to do the count, that how many of these bigrams appear in sentence 1 versus how many of these bigrams appear in sentence 2. And now the representation is different. For the first sentence, it's column 1 and 4. For the second sentence, it's column 3 and 7. So using bigrams, we are able to differentiate between these 2 sentences. We are able to capture some of that context that was getting lost in unigrams. So that is good. We are able to get some context. And you can imagine if from bigrams we go to trigrams, 3 words at a time, we may be able to get even more context. But I think some of you may already be starting to see the problem here, that the more words we take together, we get into the permutations issue. that as we start taking two words together, our number of combinations grow a lot exponentially. Three words together, they explode even further. It's really the number of permutations, n words taken are at a time. In English language, there are approximately 171,000 words. So right now we were just looking at a couple of sentences, but when we are actually looking at documents, any English word can appear in that. So our simplest matrix will probably have 171,000 words if we are looking at unique words. If we start looking at bigrams, that is considering two words at a time. So that's a permutation of 171,000 taken two at a time, which is approximately 2,924,000 combinations. And if we start looking at three words at a time, it's about 500,000 quadrillion combinations. So even though we are able to get more context if we look at pairs or trigrams or n-grams, our matrices or our data starts to explode. So that's a kind of trade-off that we need to make. That how much do we need context versus how much do we need to keep the data in a manageable format. Now you may ask that is there a solution that may cover all these points, that can keep the size limited and that can also give us all the context? Well, if there was such a solution available, then people like me will be out of a job and you will probably not be listening to this lecture, because this human element, this element of understanding the domain and then making these decisions, making these trade-off based considerations is why it's the role of a human being is so important in the job of a data scientist. Otherwise, if everything could be built into a machine algorithm or a function, then this job wouldn't be that important. So some considerations to understand context versus the size of input data. Then there is another consideration when we are looking at words. Not all words are equally important. So for example, let's say you are looking at a Google document, you're looking at just Google and you enter the word this, THIS this. Almost every document in English would contain the word this. As opposed to if you are looking at a word, let's say feature. How about feature? The word feature is much more rare than the word this, and the word feature is probably more capable of bringing you up or searching you the documents that you are looking for in, say, in feature engineering, on the topic of feature engineering. That is to say that all words are not equally important in recognizing certain documents. How can we mark this relative importance of different words for different documents? So this is where we are right now, term frequency, the number of times a particular word appears in a document. That's what we were looking at. And then there is an additional part that we can add to it, which is called inverse document frequency, which is basically a measure of how important this word is to the document, or how often this word appears in these documents. So inverse document frequency is the total number of documents divided by the number of documents in which this particular word appears. Let's look at an example. Let's say we have 5 documents total, and there is a word 1, just using a generic tag, it could be any word, but word 1 appears in all 5 documents. And there's a second word, word 2, which appears in only 1 document, which means that word 2 is a lot more capable of identifying a document than word 1. If we calculate the inverse document frequency for these 2 words, so since word 1 appears in all 5 documents, so total number of documents is 5, divided by the number of documents in which word appears is also 5, so 5 divided by 5 is 1. Whereas for word 2, again, the total number of documents remain the same, 5, but now this one appears in only 1 document, so 5 divided by 1, which is equal to 5. So inverse document frequency of word 1 is 1, and inverse document frequency of word 2 is 5, which is basically saying that word 2 is 5 times more capable of identifying a document than word 1. Another way to say that is that word 2 is 5 times better a feature than word 1. We combine both these two aspects, term frequency, inverse document frequency, TF-IDF. You might have heard this term. This is one of the most common and widely used technique of doing feature engineering on text. So TF-IDF is simply a multiplicative factor of the two things we have seen before, the bag of words or the term frequency multiplied by the inverse document frequency. I have a couple of examples of this here. This matrix is the same that we were seeing in the a couple of slides before. So what will be the TF-IDF of the word long in review 1? All right, so we say, okay, in review 1, the word long appears 1 time. So the term frequency of word long in review 1 is 1. And what's the inverse document frequency? So that means what's the total number of documents? 3. And how many documents this word long appears in? Again, 3. So the inverse document frequency is 3 divided by 3. So the total TF-IDF score of the word long for review 1 is 1. Taking another example, what's the TF-IDF of the word spooky given review 3? So spooky appears once in review 3, so its term frequency is 1. For inverse document frequency, again, total there are 3 documents. However, spooky only appears once. So 3 divided by 1 equal to 3. So the TF-IDF scores of these 2 words in documents are different. So instead of just having a naive count, having the TF-IDF based numbers in the matrix provides more context, more information, and more signal on the relative importance of different words in a document corpus. All right, let me just summarize what we have talked so far, then we'll move on to categorical features. So we have text, we want to convert text to numbers. The easiest way to do that is to create a matrix, columns each word, and rows each sentence or each document have a simple count. However, the simple count has a couple of issues. One is that simple count loses context, which comes from a group of words. And second is simple count is not giving us the relative importance of each of those words. If you want to have more context, you may want to go to bigrams or trigrams with the understanding that that explodes the data. So we need to make sure we are making the right decision given our context and our problem statement. And as far as the relative importance of different words is concerned, that's where the count of TF-IDF comes in. A very popular, very prevalent technique used in the industry.
So Bushra,
please.
I'm not from the field. I just want to understand. For this example, for instance, the word spooky is 3 times stronger than the long, or? Yeah,
correct. The word spooky is 3 times stronger as a feature than the word long. Go ahead. I think there was another comment.
Okay, because it appears less than the document long.
Yes, so because it appears less, so it can give a stronger signal to which document it belongs.
If it appears everywhere, it's featureless. So
exactly.
It's like meaningless.
Meaningless, exactly.
Yeah, okay.
Featureless is a good word to say that. If it appears everywhere, it's really featureless, not giving us much importance there. Cool.
Okay.
The third category of features we will briefly discuss are categorical features. So categorical features are also text-based features, but they are not free text. So text-based features are simply any English document is a text-based document, or any other language. I'm just using English because it's easier to give examples there, but any other language is the same thing. Categorical features have a fixed list of values, valid values, like a list of all countries. That's a categorical feature, but the number of countries is more or less fixed, like 130, 140. Similarly, maybe a list of cities in a particular country, or list of colors, a list of famous movies, list of actors, things like that. So they are still text-based, that is, they belong to a certain language, but they have fixed values. They are not free-form. So how do we convert categorical variables into numbers? The simplest encoding or simplest way to translate them is called label encoding. And the code is from scikit-learn. You can simply ignore that. That's not important. Let's say we have a feature, we have the category color, and we have 3 values, red, green, and blue, which are listed at the bottom. So the simplest way to convert red, green, and blue to a number is say, sure, we say, we assign them 0, 1, and 2. Blue 0, green 1, red 2. And I just randomly assign them. It doesn't mean that red has to be 2. Red could be 0, green could be 2, blue could be 1. But we look at all these different values of a category and we simply assign them a number in increasing order starting 0. That's simple, that's easy to do. However, it has one issue. And that is something I alluded to in the beginning of this lecture, is that the machine learning algorithms try to mine or look for as much information as they can find. So that's why we want to limit the input data to the relevant information. So here the issue becomes that the machine learning algorithms look at 0, 1, 2. It said, okay, these 3 values are probably unique, but 1 is greater than 0 and 2 is greater than 1 and 0. So probably red, it means something better than green and blue. So the machine learning algorithm will automatically try to find a ordering relationship between these 3 values where none exists. We just randomly assign them 0, 1, and 2. If we say, okay, we should assign them 0, 1, and 2, we can assign them something else. How about 130 and -4? Sure, they are not in a certain order, but they still have a certain ordering relationship. One number is higher than the other 2. This may become an issue. Before going into what we can do to resolve that, this may not be an issue if indeed these labels had a relationship, an ordinal relationship between them. For example, let's say we are looking at the categories of a review, which is highly satisfied, satisfied, dissatisfied. Now, these 3 labels do have a relationship or an order or a certain order between them. Highly satisfied is rated higher than satisfied, which is better than non-satisfied. So if we had those 3 values and if we assign them value 0, 1, and 2, that makes a lot of sense. But perhaps not for colors, perhaps not for countries, perhaps not for cities. So what do we do? How do we deal with those labels that do not have that kind of implicit ordering relationship? The second encoding or labeling technique that is used more widely than label encoding is called one-hot encoding. And in one-hot encoding, we again create a matrix and we have as many columns as the unique values of the categories. So for the category color, we currently have 3 unique values, red, blue, and green. So we will create a matrix with 3 columns, one corresponding to red, one corresponding to green, one corresponding to blue. And then we mark 1 whenever that particular value is present. So whenever red is mentioned, and my apologies, this is upside down. So the red is the final column. Whenever red is present, it's the 3rd row. Is red would be 1, green would be 0, blue would be 0. For green, red would be 0, blue would be 0, but green would be 1. And for blue, red would be 0, green would be 0, and blue would be 1. So it's I need to correct that. The rows are in the reverse order. But you get the idea now that we are not using different numbers. Each of this category is, all of these categories are represented by a single number 1. It's the position of the number 1 that determines each of these unique values. This is called a one-hot encoding, coming from engineering discipline. One hot means only one wire is hot or only one wire is live, which means there is only one of the values which is 1, all others are 0. So now with this one, there is no ordinal relationship. All the ones that are present are mentioned by ones. It's really the relative order of that one. Where is that one present in that entire matrix that marks a particular category? So this removes the issue of the inherent order between different categories. And it introduces the issue again of increasing the size of the matrix. So currently we had 3 values, we have 3 columns, talking about again number of countries, 130 plus values. That means that we are using a matrix with 130 columns, and at a given time, only one of the column will have a value 1 and all other will have value 0. That creates sparse matrices for us, large matrices and sparse matrices. And large, sure, it's a consideration as well for algorithms, but sparse matrices is more of a mathematical consideration for algorithms that deal with matrices. Sparse data creates its own set of problems, which I'll not go into a lot of details right now, but it's good to know the trade-offs here as well, that we can use a very simple encoding like label encoding, but then we should be careful about the inherent ordering relationship that that might be deduced from there. Or we can go for one hot encoding that will save us from the first problem, but might introduce problems of its own. And again, the question might be, can we have a solution that deals with all the problems? No, because then again, you wouldn't be listening to this lecture and I wouldn't have a job, or everything would be coded into computers and world would be a great place. Summarizing these, the things that we have discussed so far, starting from the very beginning, machine learning algorithms are there to determine various relationships between pieces of data. Data could be number, text, videos, pictures, audios. However, all machine learning algorithms under the hood are mathematical formulas, and mathematical formulas deal with numbers. So everything related to data has to be converted into a numeric format in order to be fed into that algorithm and give us some predictions. So then how do we convert various aspects of data into numbers? And we talked about 3 different types of data. One is data which is already in a numeric format, but that's not the end of the story either, because then we need to see what is additional information here that we can get away with. What's the minimum set of information that we need to give to the algorithm? Is magnitude important, or can we standardize it to a certain bucket? Is scale important, or can we create bins out of it? What is the probability distribution of these incoming numbers? Do they conform with the expectations of the mathematical formulas or not? If not, then there are ways to convert the incoming data from one distribution to another. Then text-based features, which are free text documents, you can think about, or web pages. So how to quantify them into numbers? The simplest technique is bag of words or term frequency, which is to count the number of times a word appears in a document. That has the caveat that a single word loses context. So we can start putting together groups of words, but then we should be aware of the permutation exploding issue. The other thing is all words are not created equal, especially in the set of documents we are looking at. So how can we assign a certain importance to a word? And that we do by the inverse document frequency ratio calculation. The third set of features we looked at were categorical features, which are also text-based or language-based, but they have a fixed set of unique values. How do we convert those into numbers? First is simply start assigning random numbers. And that may be okay for some cases, like we discussed the rating of a review or something like that. However, if we just assign the numbers, the machine learning algorithms will infer ordinal relationships out of those if the numbers are different. Then the alternative to that is one hot encoding, in which all the numbers, all the categories are represented by 1, but now we have 1 column per unique value of the category. So our matrix increases in size and it becomes more sparse. However, it does away with the ordinal relationship. So a lot of trade-offs, and that's why machine learning engineers or data scientists spend 80% of the time in feature engineering, because they have to deal with all these different trade-offs. They have to understand the domain or the context well enough to know which side of the argument or which side of the coin to favor when they are making all these different decisions between all these different techniques. So this was just touching the tip of the iceberg. There are entire courses on the topic of feature engineering, but I just wanted to keep the content to a beginner-friendly level so that anyone can follow what we are discussing and anyone can get an idea of how and why this becomes so complicated. My LinkedIn and my Twitter information is here. And sir, if anyone reaches out to you for my email, you are welcome to give it to them as well. Any question that you may have on the topic of feature engineering, data science, or I didn't talk a lot about myself, but even on my background, if you have any questions, I'll be more than happy to answer that. So back to you, sir.
Thank you very much, Bushra. Wonderful speech, really. Very informative. I'm not from the field, but I learned a lot. So if you have any questions and comments, Dr. Bushra is ready to answer, I guess. I have my own notes, but Professor Yasemin would like to thank you. Okay, Güzin, if you have the microphone, you can ask your own question, or I can read it for you. Güzin is... Güzin?
Good evening.
Hey.
Do you hear me?
Yes.
Yes. First of all, thank you. That was very interesting for me. And it's very good to hear such things because I am first of all, I'm from Transportation Division of Yıldız Technical University, and I'm dealing with data a little. And
Nice.
I wonder the difference between the neural networks and feature engineering, for example, or other techniques such as the decision trees, etc.
Sure.
Because
sure.
This is the first time I'm hearing the feature engineering, and I'm trying to put them in their right places.
Yeah.
And thank you again, and thank you, Murat Hocam, for that good meeting. Thank you.
Absolutely, I can help with that. And thank you for asking that questions, because sometimes people like me who are so embedded into the field, they forget to understand or mention a few things that comes like, oh, that's so obvious, but it's not. So neural networks or decision trees are names of machine learning algorithms. Or machine learning models. So neural nets is one, decision trees is another. Then there are a lot of other techniques as well. There are random forests, which you might hear a lot about. Then there are gradient descent and other techniques. So those are algorithms or the models of machine learning. But each of these models at the under the hood are different types of mathematical formulas. So neural networks are a different set of mathematical formulas as opposed to decision trees, which are a different set of mathematical formulas as opposed to random forests, so on and so forth. But all of these are mathematical formulas, and all of them will need their data in numeric format. So feature engineering is a pre-step for all these algorithms. No matter which algorithm you use, whether it's a neural net or decision trees or random forest, you will need to convert the data into numeric format in order to feed it to these algorithms. So feature engineering is a common pre-step or a prereq for any algorithm or any model.
Okay, thank you. Then we prepare the data in numeric form by feature engineering, then use it in the other models.
Yes,
okay,
absolutely.
Okay.
Absolutely. Yeah.
Thank you. Thank you very much.
Thank you. Another question from Nisa. She's asking if this is the algorithms that is used for the Google Translator.
Yes. Yeah. So Google Translate is at its very core is something called CNN. Not the CNN news channel, but it's called convoluted neural networks. And those are advanced mathematical formulas or very advanced machine learning models that are used. However, for those as well, the pre-step or the prereq is feature engineering. So that is done in any machine learning algorithm, in any machine learning task. Feature engineering is a common step. And then once the features are converted into numbers, then we feed it into different algorithms. CNN, convoluted neural networks for Google Translate is one of those.
Okay, Yasir would like to ask, if you have a microphone, Yasir, you can ask for yourself or I will read it for you. Good evening, Professor Bushra. I have a question. In the beginning of the lecture, you mentioned that we shouldn't feed our algorithm with too much data, Okay, so what I want to ask is there a way to find out how much data we need for a machine algorithm? I mean, do you use a technique for, I guess, deciding the optimizing binning size or something?
Sure. That's again an excellent question. The short answer is that, which is not the best answer, but it is that it really depends on the problem that you are trying to solve. Again, I'll go back to the thing that I have said a couple of times, that if it was an easy determination, then humans would be out of the picture from data science. But the reason this field is going to remain as is for at least the next few years is that there is a lot of human decision making and this trade-off kind of decision making that machines are not yet capable of. However, I can give a couple of pointers, things to consider. One is the basic one, which comes in computer science and pretty much any trade-off, is the memory considerations. If you are running a machine learning algorithm on your laptop versus you're running it on your lab machine in your university, or if you're running it on a dedicated cluster, which is just provisioned to run machine learning algorithms, the memory capacity of these three machines or these three setups will be different, and that can determine how much data they can handle or how aggressively you need to do feature engineering or not. And second is, of course, the runtime. The memory is one thing, but even if you have all the memory in the world, most of these machine learning algorithms do an exhaustive search. So the more combinations you provide to it, the exponentially more combinations they have to look towards to find the optimal solution. So with just one more feature or with just one more unique value of feature, sometimes the runtime increases by two-folds, and that may become impractical after a while. So the physical constraint, the memory constraint, or the runtime constraint, the power of the machine that you're using is certainly one. And the second is how much can you wait for each run, because it's not that you run the algorithm once, you run it once, you see the numbers, you're like, maybe we need to adjust this thing, and then you run it again. Usually you run your algorithm hundreds of times before you reach a result that you are comfortable in presenting to other audiences. So the runtime becomes another consideration.
I have a question, maybe combining with this question also. You talk about two types of binning, right? What was that?
Fixed and adaptive.
Type of binning and adaptive binning. So I'm also kind of using it. I'm data analyzing from the satellite and modeling it for the galaxy emissions, kind of.
Nice.
So, what is your opinion? Is there adaptive binning is superior, or can we say that before handling the data, or depends on the case? I mean,
yes, it depends on the case, but I will share my personal experience on adaptive binning. I have found in our use cases, we have found those to be more useful adaptive binnings, where we try to divide data into either equal proportions or divide data into even a certain scheme. So for example, I'll share that. So we analyze data of a lot of physicians, doctors, and one of the feature for those is the age of the doctor. So of course, age could be by life expectancy from 0 to 110. I'm just picking an average number. So one way could be that, okay, we will make it into 11 bins, 10 years each, and then try to analyze that. That may not be the best binning scheme, because probably there's not going to be a doctor less than 10 years old, probably not even less than 20 years old. So that may be one of the cases where fixed binning may not be appropriate. Adaptive binning may be appropriate, that, okay, how about we divide this age group into 4 groups where each group has equal number of physicians. That could be one way. The other way could be that we define the limits ourselves, that, okay, we will quantify all the doctors less than 25 years of age, then 25 to 35, then maybe 35 to 45, and maybe 60 and every age beyond. So that's a scheme which is neither fixed nor adaptive, because it does not have a fixed criteria to it. It's just something which is very domain specific. But however, making bins is better than not making bins because you're limiting data.
Yes, in our case, the high energy physics case, adaptive binning looks like more it gives us more fruitful results, I guess, more scientific, the physical meaning.
Yes, quantile space, yes. 4 bins, each with 25% data, or maybe more than that, but 1 quantile per bin, yes, absolutely.
Next question is from Emine, if she has the microphone set up.
Yes.
We are with you, Emine.
Okay, thank you for your presentation, sir. You said that if there are many categorical features, to prevent the machine from sorting between features, we can use one-hot encoding methods. But also this increases the size of the matrix too much. So how we can handle this problem? Can you propose any other encoding methods?
Sure. So there are a couple of improvements which are made, or I shouldn't use the word improvement. What's the right term? Some filters that have been proposed on top of one-hot encoding. For example, we don't need all the combinations. Let me, give a very simple example here. So here, if we have, say, these 3 categories, if we know that what red and green looks like, that is, if we know the first 2 rows, we can automatically deduce the 3rd row, because we can only have once in every row and every column. And if we already have the first 2 rows, we can say, okay, the 3rd row will have 1 in the very first column. So that's just one technique of filtering, and there are many others as well, that we still use value 1 to determine a particular unique value, but how is it present? There could be certain deductions that can be made from certain set of rows, that how other set of rows might look like. So it reduces the number of rows that needs to be present in the matrix. The number of columns, unfortunately, have to remain the same. And then the other way is this one uses mathematical deductions. The other one is that we may be able to divide the set of unique categorical variables, and again, perhaps bin them. Do we need signal on each of these unique values, or just a signal on a set of these values would serve our purpose as well? That could be another thing to look at. Third could be, can we do probably a mixed technique, that some of the categories could be simply labeled with the label encoding, and others could go for one-hot encoding if they are more important. So various type of trade-offs.
So it depends on our purpose.
Yes.
Okay,
unfortunately, that's going to be a common answer to a lot of the questions. Yeah. But depending on a particular case, if you're working on any particular problem, we can just sit together and then brainstorm on how to best deal with a particular situation. Mm-hmm. But generic guidance, unfortunately, it's not a fixed set of things to try.
Thank you.
Thank you, Emine. Is there any more question or comments? Okay, Ahmed would like to ask a question. Ahmed? Yes.
Hello, do you hear my voice?
Yes, perfect.
Thank you for your presentation. It was really informative. And the question I want to ask is, actually there are 2 questions, but the first one is about label encoding. For my project 2 lecture, I was working with this diamond data sets. It's a very popular, you might know. And for example, there are different categorical variables like cut quality of the cut, fair, good, very good, premium, and ideal. The problem is that if I give from 1 to 5 the new numbers for these categories, because there's a like one is the better than the other. I couldn't find the right range of numbers that I should give to them. Like if I give 1 for fair and 5 for ideal, then it means ideal is 5 times more important. But if I give like 5 for fair and 10 for ideal, then it means ideal is just 2 times more important than the fair. But the problem is that I don't know much about the cut quality of diamonds, so I'm not sure how to give numbers to them. Do you have a solution in this kind of problems, or is it just I need to just try out and find for my own?
First of all, that's an excellent example where label encoding is very appropriate, that we don't really have to do one-hot encoding. Label encoding will serve the purpose. How important the relative categories are, that's a domain-specific question, unfortunately. So if really it will be best if you can have a conversation with someone who is from that field or who knows more about the various gemstones. I personally know very little about diamonds, but that's one place where the the domain expertise comes into play. So how important one category should be as compared to another, that should come from a domain expert.
I see. So we can't find it by ourselves just by trying to see the results of our machine learning algorithm. Like if the algorithm is guessing better, then maybe we are on the right track. Is it possible to say something like that?
It might be, but then the question becomes that is the algorithm becoming better at the expense of bad data? So for example, we can create a perfect data set that can give us perfect results, but that's not the intention, right? The intention is that the model accurately reflects the real world data or the accurate data. What is accurate in this case? Is it that the top rate is 2 times better than the bottom rate, or is it 5 times better than the bottom rate? Whatever is more accurate should be the data that should be reflected for the model, and then whatever results we get. Because if we start changing our data or the relative importance of our data to get the right results, that's a very slippery slope, as you can imagine.
I see. Thank you. My second question is about how can we find real life data? Because for my graduation project, I'm trying to find real world data, but which is not very easy, because actually our teacher said that you should find it from the companies if possible, which I haven't found yet, unfortunately. And they don't want to share much information about their work, as you can guess. So which sources can I use in this scenario?
Yeah, you're probably getting it directly from the companies may not be practical. What could be practical is that some of the projects that are, especially the open source projects, they do publish their data sets. The one thing that immediately comes to my mind is the website Kaggle. They have a lot of data sets that they publish of different sizes, but they are mostly real world or real data values data sets. There are a couple other websites as well. So please do reach out to me after this. And if you're looking for data in any particular domain, like maybe medical data, or a lot of people were doing work on COVID related data as well in the previous year or so. So if you let me the exact domain that you're looking for, I may be able to suggest a few other websites as well. But Kaggle is a good dump of almost all types of data.
Yeah, we worked from data that we took from Kaggle before, but this time, like the teacher says, like you need to work in a more complex data, which like you will normally face in real life. You know, they are not very easy to handle. So we are trying to find one. Thank you very much.
Thank you, Ahmed, and wish you best of luck on your research. And another question is from Ömer Faruk.
Dear Anjum, first of all, thank you very much for your conferencing. And I'm a PhD candidate dealing with deep learning research on biomedical data. And as you already realized, even the recent years, there are lots of tutorials, something like machine learning in 1 week, or any kind of programming language in several hours. But as a field worker, we know this is not so easy. Otherwise, you have to dive deep into try and fails, as you explain all of the example like encoding or any kind of labeling. My question is, which courses or which areas should be learned first for diving deep into, for especially data enthusiasts? Thank you very much.
Sure. And good luck with your PhD research. I have been a PhD student myself, so I know how exciting and at times painful those years become. So all the best to you. As far as the technologies or courses are concerned, one is that if you're trying out various types of machine learning algorithms, both Python and R have enthusiast. Some people like use R more, other people like to use Python more. But my personal experience has been that Python has a lower bar to entry as far as doing data manipulations and using various of the algorithms available for testing things out. So that's one. If you don't have much know-how of Python, there are a number of courses available online, and just a few hours into it, you will get the basic know-how or the level of familiarity you need with the language to run a few algorithms. Also, there are a lot more tutorials and examples available with Python as compared to R. So Python is certainly one thing I would recommend. Second is, if you want to run the algorithms, Google has this Google Colab. It's a free service. It also has its paid tiers, but if you have any if you have a Google account, then Google Colab comes with it, just like the Google Drive comes with it. And Google Colab lets you run experiments, gives you certain CPUs based on cloud, and gives you certain memory and runtime, and you can run those algorithms there and see what type of results you get. And then if you need more powerful algorithms or more powerful machines, then you can get a paid subscription as well, but that's only for extreme cases. So this is Google Colab is a better platform to start exploring data than just your machine, because it does give you more power than just a simple machine. So I would say technology-wise, Python, certainly having a good know-how of that helps you start on this journey. And then as far as where to run the programs exactly, Google Colab provides a free and a very easy to use platform to get started there.
Thank you very much.
Thank you. Do we have any more questions or comments? I guess we are done. Everything is clear. But if not, I would like to thank Bushra for wonderful, informative presentation. And okay, şey mi var? Bu arada hemen atacaksam.
I will pop up a survey.
A quick survey for the presentation. So you manage that, Ömer, and the attendees will answer. And I will like to make my closing speeches. And I would like to thank again Bushra for this wonderful, informative presentation. And on her behalf, I would like to celebrate the importance and significance of women in every person's life in a week advance of the International Women's Day. You know, it's celebrated on the 8th of March, but I would like to celebrate your International Women's Day because you are really wonderful, successive woman, Bushra. Thank you for the presentation.
Thank you, Sarah. Yeah.
And we would like to meet you all for the next week again, Grad Talk at 5 p.m., I guess. Thank you, everyone. Good evening, and have a nice day in San Francisco, Bushra. Thank you.
Thank you, sir. All right. Thank you, everyone. I appreciate your time. Okay. Bye.